Hi, my name is Kevin Townsend, and thanks for coming to my talk. And we'll be talking about Trusted Firmware M and some of the integration work that's happened with Trusted Firmware M in the Zephyr project. A quick agenda that we've got here. My name is Kevin Townsend, as I mentioned, and I work with Linaro, and we've been quite involved, obviously, with some of the integration work around TFM and some upstream development. And I'll just try to run you through basically some of sort of not only what's been integrated into Zephyr, but just some of the features that the TFM sort of brings to the table and why we think it's a very important project. So first, though, a word of warning. Just because of time limits, this presentation is really a very high-level overview of TFM and Zephyr. I just can't really go into a lot of details on some of the specific features that the TFM offers, but hopefully, if after watching this presentation, you're more interested in TFM or you're more aware of some of the functionalities that are in the project, I've tried to leave some breadcrumbs that you can follow up and sort of dig a bit deeper on your own time. And obviously, I have to leave that as an exercise to you as the reader. But yeah, hopefully you can at least find some details to know where to go from here. So what is Trusted Firmware M? You may or may not be familiar with it, but TFM is an open source reference implementation of something that's called the Platform Security Architecture IoT Security Framework. Big fancy word, lots of acronyms to memorize, but you can Google around and see what PSA is, but basically it's something that aims to solve a lot of the most common security issues in IoT devices out of the box and give you a very secure foundation upon which to implement sort of secure IoT solutions. Its provenance sort of comes out of another project called Trusted Firmware A, which is basically based on a lot of Cortex-A class processors, and we're talking about embedded Linux, Android, sort of much richer, higher end systems where there were obviously a lot of security concerns around protecting the firmware, protecting secrets on devices, and that was a very successful project. So TFM sort of came out of that initiative of realizing, well, hey, a lot of this great work that happened on these bigger A-class devices, we have a lot of those same problems on smaller Cortex-M class devices, and just sort of these small, deeply embedded IoT devices. And so the two projects have sort of identified different requirements, but they've come out of the same place of just trying to give people a very secure starting point for developing secure IoT or A-class solutions. So Zephyr has been PSA certified since Zephyr 2.0 with the very first TFM release 1.0. And what PSA certified means is simply that Zephyr has gone through a certification process to ensure that it plays well with the APIs, the PSA APIs specifically, that TFM uses. And there's recertification is planned for Zephyr 2.6, which was just released last week, and the latest TFM release, which is 1.3.0, which is what we'll be discussing in this presentation. So that's a lot of talking. The big question, of course, is how does this help me? How does this relate to me? Well, basically, I think a lot of us can relate to this process that I'd like to describe here, where firmware today, the way it's developed, it's often developed in a way that you have a very monolithic binary blob. There's a lot of ad hoc development, requirements change, and things tend to be developed something like this. You'll get some requirements that you inherit from your manager or maybe some external departments. And based on those requirements, you're going to put together some SDKs and some libraries and identify some key building blocks that maybe you're familiar with, maybe you're not familiar with, but most likely you're going to take some vendor SDKs in RTOS, maybe a file system if you need to log some stuff to an SD card or to SPI flash or something like that. And you're going to basically glue all of those together and then start to work on your application where you implement your business logic. So the problem is about 60% of the way into this process, you realize, oh, I need firmware updates or some other major requirement that comes in, and I inherit some other additional feature, non-trivial feature that needs to be implemented. So what happens? I start digging around on Stack Overflow and I figure out, okay, well, if I need to have a bootloader or for firmware updates, or if I need firmware updates, I'm going to need a bootloader and I'm going to need an IP stack to download that. And I'm going to have something on top of my application code in the RTOS to manage those firmware updates. And so you add those extra components into your monolithic project. About 90% of the way in, of course, getting close to the deadline now, you realize that you actually care where maybe those firmware updates come from, and that you actually can't just download them from any arbitrary server, and you actually need to care about, say, TLS. So now you're starting to feel the pressure of your deadline, but you have to figure out, okay, well, how do I get a connection to an HTTPS server using TLS? So you start digging around on Stack Overflow and looking for just random last-minute solutions and crypto libraries that are suitable for embedded devices. And you find a slightly better bootloader and you tie it all together and it sort of works. 98% of the way in, of course, you hit a brick wall and you realize, well, actually, these random components off Stack Overflow and whatever, the first thing that you came across Googling that you got to work, it actually doesn't really work. And so you now, with better information at your disposal and a better understanding of the requirements and the trade-offs involved, you pick better components this time. So maybe you're going to go with something that's sort of tried and tested, like Embed TLS for your TLS stack, and you'll pick a secure bootloader. But at this point, you have an enormous amount of pressure because you're close to your deadline and you just need to ship the thing. And you take components that you believe are more reliable, you glue them together, it works, but you haven't tested things as well as you should have. You don't know if you've got the configuration right. You don't know if you have the cryptography settings right or the right ciphers or exactly the right settings on your device. So what happens is, a little bit past the deadline at 110%, you ship a house of cards, just because you have to ship something and you just kind of cross your fingers and hope for the best. I'm sure this is something we can all sort of relate to. And so what you have is something that I like to call firmware mystery soup. It might look decent. You might think you have something that sort of mostly works and meets the requirements you have, but you couldn't test the temperature before you serve it to your clients. You don't know if they're going to get burnt. You don't know if it's going to be cold. You have no idea. And more importantly, you don't know if any of those random ingredients that you threw into this firmware mystery soup, if they were out of date, if they even work together at all, if people are going to get terribly sick from eating this soup, whatever. Please just, if you can avoid it, don't serve firmware mystery soup. So this approach obviously has a number of evident problems around it. Obviously, security concerns often surface far too late in the development process to be adequately sort of reviewed and vetted and to identify appropriate components to solve those concerns. The expertise that's required to select an appropriate crypto algorithm and an appropriate implementation often just aren't there because, again, they come so late in the development process, and you end up with roll your own security, which is exactly what you want to avoid in any situation. There's no isolation of your device secrets and your resources. Again, with this sort of monolithic ad hoc solution, when you have just this one binary blob mystery firmware soup, any vulnerability in your firmware is probably going to give attackers access to everything else in the firmware. And that's something obviously you want to avoid if you don't want to end up on the front page of Hacker News or in the newspaper about an IoT security leak. You have risky all or nothing firmware updates. Again, just having this monolithic binary blob. Key management and key storage or storage of secrets is often an afterthought. So you probably have hard-coded keys in your firmware that you're not able to update without doing a firmware, updating the entire firmware binary blob. Things like audit logging and the security analysis after an incident occurs, they're usually a distant afterthought, and you only realize those things are important when you've already had a security incident and it's too late and you don't have the kind of audit logging and traceability that you're going to want to identify exactly what happened and what went wrong. Non-security engineers are probably unaware of a lot of the common attack surfaces and vectors that people take advantage of in IoT projects. And security is just a difficult field. It's really hard to stay abreast of sort of what the most common vulnerabilities are, what you need to take into account, the common situations you should avoid. Just they're things that non-specialists have a really hard time keeping up to date on, and there's just so many moving parts in general in development that you can't specialize in everything. So coming back to the question, how does this help me? I'm sure we can all understand at least some of those points that I've tried to illustrate as shortcomings in the classic embedded IoT firmware development process. So what if someone could give you isolation of secure and non-secure resources on your embedded device, modern embedded appropriate crypto? And embedded appropriate is important there because we have very limited sort of resources and processing power. So you want to balance security with just the processing capabilities that you have. Reliable secret management and storage of those secrets on your device, firmware verification and encryption, protected off-chip data storage and retrieval. So many MCUs today have mechanisms perhaps to protect on-chip devices, just so that it's a little bit more complicated to get access to those things. But what if you have to store devices off secret? Or what if you have to store secrets off device? That's often an afterthought, and you're going to want to have to deal with things like encrypting those secrets or ensuring they're not tampered with. Proof of device identity. And this is also something that's an afterthought. Maybe I have a server sitting on some backend, and I think my IoT device and the server are talking to each other, but how do I know the device I'm talking to is actually the device that it's claiming to be? That's something that I think more and more we really need to take into account in sort of production environments. Audit logging, which we already discussed, who accessed what and when and in what order, just to try to understand when something goes wrong, what happened and how to address that. Obviously, we can give you some extra acronyms. It just kind of goes with the territory. And most importantly, how can we have these things with a minimal learning curve, just understanding that not everybody can become or be a security expert sort of from day one. So Trusted Firmware M aims to bring you sort of just what you need after all of that dodgy mystery firmware soup experience, which we served out last time. And that's hopefully something that you'll see is a fairly well-balanced and, best of all, free lunch. And I'll try to explain sort of why TFM delivers a very different experience than maybe what you've traditionally delivered with this monolithic approach. So TFM is based on something called a root of trust architecture. And this is a very important concept. If you're not familiar with the idea of root of trust, it's a very common concept in security engineering. You'll want to Google it and you'll want to try to understand a little bit of what that means. It's a very important term to wrap your head around. So root of trust, and some of us will understand this better than others, but root of trust is all about boundaries. And that's just, in any good relationship, of course, it's all about boundaries, and firmware is no different here. So a root of trust architecture allows for hierarchies of trust from most trusted to less trusted to entirely untrusted. And you have sort of gradients of trust inside your firmware and in the images you deliver and in the access and allocation of resources in your device. And it's just a reality that you always tend to have more and less trusted components in your system. And sort of TFM, based on the root of trust architecture, gives you a framework with which you can safely execute untrusted code or access resources in an untrusted environment without compromising the more or most trusted aspects of your overall firmware design. So TFM provides you a sound foundation upon which other structures can be built out of the box. And we'll go into some details here on what that means and why that is. So everything in your system starts with secure boot. If you don't have secure boot, you have no security in your system. So the first thing that TFM sort of brings to the table is a very robust secure bootloader. It's based on an open source project called MCU Boot. But what secure boot brings to the table is that it allows you to ensure that any of the firmware images that come later in this sort of chain of trust are trusted images that have that are signed with a specific image, signed with a specific set of keys, And the public key to verify that is burnt into MCU Boot, so that you can be sure that the images you run come from a reliable source, and also that they haven't been tampered with, that the images are not just signed, but also hashed. And we'll see that a bit later. So this sort of entry level, this entry point into running secure firmware in PSA terms is called the PSA immutable root of trust. Immutable simply because this is sort of the one thing that you can't change in your system, and it's the most trusted component, and it contains sort of the fundamental root of trust of the rest of the system. So you can look at MCU Boot, specifically the project, if you want to look at some documentation and some source code. We don't have time to really go into exhaustive detail about this, but just some high-level details is that MCU Boot has a secure bootloader. The public signing keys are baked into the bootloader, and those are used to verify the secure, non-secure, or whatever other firmware images you start to execute coming out of reset. All of those subsequent images that you run are all hashed and signed. And that's very important because it makes them tamper resistant, and you can verify the provenance of your firmware images, that somebody who doesn't have the private key that you hopefully are storing somewhere secure when you create your firmware images. Without that private key, no one will be able to impersonate your firmware images and sort of run malicious firmware images on your TFM-based device. Also importantly, the secure and the non-secure images, they're both separate images, and they can both be signed using different keys. So there might be a situation where you have a secure firmware image that's developed by, say, a silicon vendor, or by you as a manufacturer with a trusted internal team, and you deliver that secure signed image to an OEM provider or to a customer, and that OEM provider or that customer develops a non-secure image that you don't trust to the same extent, and then they can sign their non-secure image with a separate key. And so you can verify the provenance and that neither of these images have been tampered with separately. And MCU Boot is able to deal with one or multiple images with one or multiple different signing keys. So you have this separation of sort of development authority as well. Some of these other details, I think, like the way flash layout works with MCU Boot, those are things that you can verify looking at the MCU Boot website. Yeah, just one other high level point to notice with Secure Boot as it's implemented with TFM is that it also, not only does it give you the ability to sort of sign, hash, and verify your images, you can also encrypt your images optionally. So if I need to take my firmware image or images and release those onto just some open web server, or maybe a Git repo, or just some sort of public server, I don't necessarily want to release those images in some open form. So MCU Boot and TFM give you the option to additionally encrypt those images. And the bootloader can, depending on the configuration that you set up, of course, during the firmware update process, it can decrypt those images. So it also takes into account just the need to maybe publish firmware on a public server without making it easier than strictly necessary for people to reverse engineer or decompile your firmware images based on what you publish. So the secure boot process basically looks something like this. Again, we don't have a lot of time to really dig into this extensively, but you can sort of see basically how the secure boot process works. Starting here at the reset vector, what happens is MCU Boot will check in the secondary image slot to see if there's a new image found. If that image is found, it will verify the hash and the signature of that image that you're trying to update to based on the public key that's stored in the bootloader. If the hash and the signing algorithms aren't good, the image will be rejected, and you will continue to execute the last known good image. If the hash and the signature are good, then there will be sort of a flash update process where the new image will be switched over in the place of the old image. The device will reset, and then we'll go back to this process again of coming out of reset. It will check for a new image. No new image will be found, so it will jump to the reset vector of the current verified valid image, and then start the firmware execution process, knowing that you have a verified firmware image in place at that point. So that brings us to the secure processing environment and the booting up of sort of critical systems. So the first thing that happens with TFM and sort of this trusted firmware based device is that we haven't gotten at all to the untrusted application. The very first thing you do is you start up the most trusted applications in the secure processing environment. And what that does is that gives you an opportunity to really lock down your device sort of out of the box. So maybe you want to set up the MPU, or you'll want to configure certain peripherals that are only accessible from the secure processing environment. Like maybe you have a crypto element on a SPI bus or an I2C bus, and you want to lock down that I2C bus so that only the secure processing environment has access to that. So those are all things that you will do before you hand execution over to the non-secure processing environment. And this blue section here that comes after secure boot, this is called the PSA updatable root of trust. And so this is highly trusted, but it's updatable in the sense that you as maybe new services are implemented or new TFM releases happen or new custom services are put into place, you can update that component and it can be verified by the immutable root of trust, which is your secure bootloader, based on the signing keys and the hashing algorithms that are used. So the PSA updatable root of trust is your most trusted secure root of trust. Depending on the isolation level that you pick, there's a secondary trusted root of trust called the application root of trust. And that's shown here in green. And even inside the secure processing environment, there's an option to implement two basically levels of trust, where the blue one, the PSA updatable root of trust, is more trusted, and the green application root of trust is less trusted. And this gives you a mechanism maybe to implement some custom secure services that you want to isolate from the non-secure environment, but you don't necessarily want those application root of trust services to have access to some of the device secrets that are only accessible from the more trusted PSA updatable root of trust, which is shown in blue here. And the exact level of isolation between these three different roots of trust is something configurable, and depending on how much resource and energy you want to commit to isolation and how much flash space and memory and overhead you have, you can sort of toggle up or down the amount of isolation that happens here. And we'll go into that in a bit more detail in a minute. So that takes care of the secure processing environment. And what happens after we've done all of this? We've set up our updatable root of trust. We've set up our application root of trust. The device has been locked down. At that point, and only at that point, do we hand execution off to the untrusted environment. And this is where you're going to be running, say, your Zephyr application that talks to the secure processing environment where TFM happens. And the communication between this untrusted application and the trusted secure processing environment happens using something called the PSA APIs. And these are a set of APIs that are defined as part of sort of the PSA secure IoT framework that allow you to talk to these secure services and these application root of trust services from the non-secure environment without sort of exposing more information than you need to. Usually the mechanism through which this communication happens is IPC. There are some other mechanisms you can use to talk to sort of isolate the communication between the non-secure and the secure processing environment. But generally with Zephyr, you're going to build your Zephyr application and it will use IPC, an IPC mechanism to talk to the secure processing environment using these PSA APIs. So, and the free lunch part that I alluded to earlier is that one of the good things about using TFM with Zephyr is that Zephyr out of the box does everything that you need to for TFM in terms of the build. You don't need to understand anything about the TFM build system. You don't really need to understand anything about the implementation of TFM or the secure services. All you have to do is build your Zephyr application using an appropriate non-secure development target. And all of the TFM stuff will sort of just be linked in and built and compiled for you out of the box with sort of very minimal learning curve and very little, no knowledge required of what's in this sort of secure processing environment. So very quickly, you can get up and running with something that you have a high degree of confidence in, and strict isolation between the non-secure and the secure processing environments. So just as a summary, basically this root of trust architecture that TFM provides with the PSA APIs is you avoid a lot of the most common security issues out of the box, and with a very minimal investment on your part in terms of learning curve. You have a very high degree of trust in the integrity of the system and the data that's coming off of it. You have very strict, usually hardware-based separation of resources. And I say usually hardware-based because most of the boards that support TFM out of the box are based on the ARM v8M architecture, which has something in hardware-based ARM called something based in hardware called ARM Trust Zone. And ARM Trust Zone is the hardware mechanism that allows you very rigid isolation of your secure and your non-secure processing environments. And you can Google Trust Zone and really see how that works in practice. What that means, though, usually is that a security failure in the non-secure environment is not going to compromise the secure environment. And that's why that hardware-based isolation of execution environments is very important, that you can't easily compromise your secure environment where you're storing all of your device secrets by provoking a fault on the non-secure side. And untrusted code never has access to the device secrets that exist on the secure side. Something else this architecture of TFM allows for that's extremely important is that the algorithm selection and the implementation is done by security experts. And that's just, again, as we've alluded to before, it's such a fast-moving field that most people just don't have the tools in their toolbox to not just select an algorithm, but even if they've selected a specific crypto cipher and they've identified that cipher as being appropriate for an embedded device, you still need to deal with a secure implementation of that cipher. And there are so many moving parts that the difficulty with security is that you only need one shortcoming and the whole system can come crumbling down. So by using TFM, you sort of alleviate the need yourself to identify appropriate algorithms and to largely verify the implementation of those algorithms, because TFM has been developed and tested and verified by a sort of respected team of security experts that have made a lot of those choices for you and implemented in what we believe to be accurate way the various crypto ciphers used. So I guess, as mentioned, selecting crypto ciphers that are robust and appropriate for embedded systems, that's a very hard problem, and that's a very difficult trade-off. And it's reassuring to be able to trust the decisions that were made, to entrust those decisions to security experts, as is the case with TFM. And we already mentioned that the secure and the non-secure images can be individually signed and developed, so that the secure firmware image can be developed by one team and the non-secure images can be developed by another team. And there's sort of this isolation of trusted parties and untrusted or less trusted parties. And this architecture just basically allows you to sleep better at 3 a.m. on a Sunday, having to worry significantly less about some of the most common security issues in IoT coming to sort of bite you in the backside. So TFM, as we've mentioned, contains two roots of trust. The PSA root of trust, and that consists of two components, which we'll get into, and the application root of trust. And I'm just going to sort of jump through this quickly because we've already covered this a little bit. But the PSA root of trust is the primary root of trust and the most trusted root of trust. And it consists of these two components: the immutable root of trust, which is secure boot, and the updatable root of trust, which is where your secure services like PSA cryptography, internal trusted storage, where all of your device secrets are held. So this is sort of the updatable component, but the updatable component that's most trusted in your system and has the highest level of access to device secrets. The application root of trust is a reduced privilege environment that still executes in the secure processing environment. and it allows you to provide sort of application-specific trusted services. So if I want to implement, again, as we mentioned, a custom secure service, but I don't necessarily want that custom secure service to have access to device secrets like my cryptographic keys, then you want to place that in the application root of trust with slightly reduced with slightly reduced privilege levels. And we'll see how this works out in sort of the next couple slides. So another important concept to keep in mind with TFM is that there's something called isolation levels. And these isolation levels define the separation that exists between the root of trusts. And depending on the isolation level that you choose and the isolation requirements that you have, one of these levels will be more or less appropriate for you. So the first isolation level, called isolation level 1, basically you only isolate or separate the non-secure processing environment, which in this case will be Zephyr RTOS, from the secure processing environment, which in this case will be TFM. So secure services on the TFM secure processing environment side, they're not isolated from each other in this case. So the application root of trust that we mentioned, it basically has no meaning here. Everything in the secure processing environment has essentially the same level of trust and the same access to sort of secure resources. So this is the simplest level. It still gives you a fair amount of protection out of the box in the sense that a fault on the non-secure side is not going to compromise the secure side, but this is appropriate for maybe the sort of the smallest microcontroller classes where you just want basically a simple secure, non-secure isolation environment. If your requirements are a little bit more specific, on the secure side, you can move to something called TFM isolation level 2. And what this introduces is that application root of trust at a lower level of trust than the PSA root of trust. So this gives you basically two distinct levels of trust in the secure processing environment. And that way the application root of trust, for example, will not have access to some of the device secrets that only the PSA root of trust has. And this is probably a very common scenario, sort of a common use case that will meet a lot of requirements where maybe if you have the need to implement a custom secure service, this is probably the isolation level you're going to want to choose. Now, if you have a need for a very secure processing environment and you need isolation even between those application root of trust services, you can move to something called isolation level 3. And this basically takes the same concept as isolation level 2, except in this case, even the secure partitions inside the application root of trust are isolated from each other. So one secure partition in the application root of trust no longer has any access to anything else, even inside the application root of trust. And obviously there's some overhead that comes with this, and this adds sort of, those barriers add overhead in terms of communication and just the requirements that need to be implemented for each individual application root of trust service. But if you need those strict requirements, then TFM isolation level 3 will provide that for you. So that's a whole lot of talking, and hopefully some of that makes sense, and you can dig into the things that are less clear sort of moving forward. But this brings us to, I think, one of the most important things in TFM, and that's the secure services that TFM brings to you out of the box. So as of TFM 1.3, which is the latest TFM release as of the Zephyr 2.6 release that happened earlier last week, TFM 1.3 brings the following secure services to you out of the box, and you can access all of these from the non-secure processing environment, of course. So audit logging, again, this is providing a level of traceability in the system to know exactly what accessed what resources and when, and from what service, and et cetera, so that you can, when something unknown does happen, there's an audit log to sort of trace back and see what happened and what went wrong. PSA crypto, and this is an extremely important service. This is basically where all of your cryptographic algorithms, all of your secret storage, and the various hashing and signing algorithms, all of your cryptographic operations will happen purely on the secure processing environment, making calls to PSA crypto. And beneath the surface, PSA crypto uses embed TLS. But this allows you for very strict isolation in the sense that I can request on the non-secure side, I can request a cryptographic operation. That request will be handed over to the secure processing environment. And for example, let's say I need to sign a specific sensor data payload that I've generated on the non-secure side. I don't want to give access to the private signing key to the non-secure processing environment in a sense, because I don't trust the non-secure processing environment with that private signing key. So what would happen is the non-secure environment will make a request to the secure processing environment through the PSA crypto API and say, here's this data, sign it using this key that's stored in internal trusted service. The secure processing environment will perform that signing or hashing or whatever cryptographic operation because it has access to the private key. And then it will give you back the results that are signed, hashed, encrypted, whatever. And at no point will the secure processing environment, the non-secure, untrusted processing environment ever have access to the device secrets that are required to sign, hash, encrypt, whatever. So that isolation barrier protects your private key at all times from the non-secure environment. You have a service called firmware update. And basically this gives you a mechanism to initiate a firmware update on the non-secure side, where perhaps the non-secure firmware image will connect to an HTTP server, download a firmware image, and then you can take that firmware image you downloaded using a sort of an update mechanism that's specific to your business unit or to your company or to an OEM provider. They can get the firmware image however they want, and then hand that firmware image over to the secure processing environment to be verified. So the hashing, the signature, and all of those things will be verified securely without exposing any device secrets, and the whole update process will be managed. The flashing of the secure firmware, the flashing of the updated firmware image will happen on the secure processing side, so that you can trust the whole firmware update process to the secure side, but it can be initiated on the unsecure side, if that makes sense. You have a service called initial attestation. And the goal of initial attestation is to solve this problem of ensuring that the device you think you're talking to is actually the device that you think you're talking to. And there's a lot of mechanisms that go into place around that process. But you can look at the initial attestation service as basically the tool in your toolbox to ensure that you're talking to the device you really think you are. And it's an important but often underestimated problem that often comes up when it's already too late, or sort of you realize the need for this often when it's already too late. So TFM brings to the table sort of a solution to a problem that you might not have even known you had until it was already too late. There are two secure storage services that TFM implements. The first of those is called internal trusted storage, and this is device secrets that are stored inside the MCU itself, usually in internal flash. This is where things like your cryptographic keys and all of the device secrets that the crypto service uses will be stored internally in the flash using internal trusted storage. There are also cases though where you need to perhaps store information or even device secrets outside of the core MCU on SPI flash or I2C EEPROM or somewhere else, and you don't have the same level of control over those external devices. So TFM also implements a service called protected storage for external devices. And protected storage gives you a mechanism to encrypt secrets that are stored off of the MCU, and also to verify that that information stored off of the MCU hasn't been tampered with. And there's a variety of mechanisms that are used to implement those things. And you can look at the protected storage service specifically to sort of see what options you have and how it accomplishes that goal of securing off MCU resources. And if you want to implement your own services, and that probably is the case at some point, TFM also gives you a template with which to create your own custom services, which will usually be executed in the application root of trust. We don't have time really to go into a lot of the specifics of how these services are implemented and what they bring to the table. But if you download this presentation, you can follow some of these links, for example, to the audit login service integration guide. And I just wanted to basically put these slides down to give you sort of some breadcrumbs so that if you're interested in a specific service, this will hopefully give you sort of a high-level overview of what the service does, some of the key configuration variables, and point you in the direction to really understand them better. So here we have audit logging. These are some of the critical links you're going to want to look at for the PSA crypto service, and that's an extremely important one to understand in any sort of secure IoT solution. The firmware update service. This is a new one, and I think it's an interesting one because it's important to be able to cater to custom firmware update processes that are going to be specific to maybe a firmware vendor or a business unit or to a company. And you want to be able to customize how you retrieve the image, but you don't want to hand the actual image update process and the flash update process. You don't want to delegate that to the non-secure processing environment. You want to be able to sort of download an image, but then verify, sort of trust but verify. Well, not even trust but verify. Don't trust, just get the image and verify it. But so the firmware update service is important, and it gives you a flexible mechanism to perform firmware updates where you decouple how you get the image with how the image is actually verified and updated. Initialist attestation, which we've already covered. What sort of, is this device the device I think it is? How do I verify that? What options do I have? And you can follow some of the links here about some of the security mechanisms that are available. Things like sending an authorization challenge to make sure that nobody is sort of forging or replaying previous attestation tokens. What is an attestation token? How do we avoid replay attacks? Things like that. So you can follow some of the links and some of the keywords here to understand what initial attestation means in the case of TFM, and what an initial attestation token is, which is an important concept to understand here. Secure storage, you have the internal trusted storage, which is for storing device secrets inside the MCU, and protected storage, which is for storing and optionally encrypting secrets or just information off or outside of the MCU. Another key concept that you'll want to dig into that we just can't go into a lot of detail here is the hardware unique key. And every device in TFM has to implement a hardware unique key that has at least 128 bits of entropy and at least a 128-bit sort of data size for the source of entropy. And the hardware unique key is extremely important because that is what some of the other keys for things like protected storage are based off of. And hardware unique is obviously the important concept here because it means that I can't just take another device, I can't just take another MCU and flash TFM and connect maybe my SPI flash that was encrypted from one device and put that on another board with a compromised secure processing environment, and I won't be able to access the encrypted information on that SPI flash because it is being encrypted with a key that was derived from the hardware unique key. Again, this is an important concept in general in cryptography. You'll want to be familiar with it, and hopefully some of the points here will give you some breadcrumbs with which you can understand why a hardware unique key is important, and also some of the key sort of macros that are used in TFM to work with the hardware unique key. And here's some pointers also on how key derivation works with the hardware unique key. And key derivation based on the hardware unique key is important. It has a number of benefits. First of all, that if you derive a key, such as with protected storage, if you derive a key from the hardware unique key, you don't need to store that key anywhere inside the flash, sort of the device's flash, even in internal trusted storage, because you can always regenerate your key based on the unique, highly protected hardware unique key. So there's a lot of advantages, not just to having a hardware unique key for one case, but deriving other keys from the hardware unique key. So key management in general, again, is a very important concept with TFM. Again, it's not something we can really go into, but PSA crypto does provide you a mechanism to also manage keys that aren't necessarily derived from the hardware unique key. Maybe you're during the factory provisioning stage, you're generating some specific signing keys, maybe to connect to a specific cloud service. And TFM exposes a way to also provision your device with those device secrets and maybe keys and store those internally inside internal trusted storage. And PSA crypto can perform cryptographic operations based on those stored secrets. And so during maybe the factory provisioning stage, or if you're doing some late binding to a cloud service, during that provisioning stage, you can do a one-time operation either to securely transfer a private key to secure storage, and the untrusted environment will never again have access to that private key data. Or maybe you just want to tell PSA crypto to securely generate on its own a private key, and the non-secure untrusted environment never has access to that private key, but then it can give you the public key based on that private key, and you can go through sort of a provisioning process in the factory or to your cloud service to be able to establish sort of some sort of identity that you can use to authenticate later with the cloud service, AWS or Google's IoT platform, whatever that might be. So there's a very rich, not only key management mechanism in place with TFM, but also the ability to perform cryptographic operations based on keys that are introduced later in the provisioning process, or sort of the provisioning pipeline. Again, this is all a lot of information, and we sort of just left a lot of things undiscussed. But if you want to get started with TFM out of the box today with Zephyr 2.6.0, what can you do? Well, the good news is you actually don't even need any hardware. Out of the box, Zephyr 2.6 supports using TFM with QEMU, including sort of managing the secure and the non-secure processing environment, isolation using ARM Trust Zone. So if you use the MPS2 AN521 _ non-secure platform as your board target, that will allow you to run all of the TFM demos and samples out of the box using only QEMU. So no hardware required. You can start developing your services and playing around with TFM as a project today without any specific board requirements. If you do want to do some development with hardware, as of Zephyr 2.6, these are some of the specific hardware platforms that have already been integrated in Zephyr and have already been integrated with TFM. So if you have any of these hardware boards, then you can run the TFM sample applications on those specific targets as well. Some of the key sample applications you want to look at if you really are interested in TFM and want to get started are, for example, PSA level 1. This is a good example if you want to understand how the PSA crypto API works, maybe key management as well. Just a caveat that PSA level 1, by the time you actually download this this presentation and start to really play with this PSA level 1 sample will probably have been renamed to PSA crypto, but it will be one of these two names. So that's a really good sample to look at just to understand the PSA crypto API. Some other demos that you might want to look at are PSA protected storage. That's a useful demo to show how you can store securely resources off of the MCU, including optional things like encryption and rollback protection, etc. And TFM also includes a large suite of regression tests or PSA API tests that exhaustively test the PSA APIs that are implemented. And you can run these regression tests or the various PSA API test suites also from Zephyr. And those are also a great way to understand just the PSA APIs and some of the features that are available to you out of the box, and just to have sort of some example function implementations. So you'll want to look at those samples if you are interested in TFM. If you want to run any of the samples, for example, with QEMU, it's as simple as just pointing to the MPS2 AN521 non-secure target. That's the target that implements QEMU, and just append your sample name with -t run. And instead of expecting that sample to be flashed to a board, West and Zephyr will take the sample and run it in QEMU, and you'll see the results right on sort of your command line, the output of the sample. To run it on real hardware, just use an appropriate target board, in this case, the LPC Espresso 55S69, making sure to use the non-secure board target. That tells Zephyr that we want to use TFM, and pass it an appropriate sample. Flash your firmware images as usual, reset the board, and you should see your TFM results. So again, sorry to sort of fly through so many things and just sort of throw so much information at you. Again, some more breadcrumbs. If you're interested in more, if you really see the value, and I really hope you do, to TFM, because I really think it's an extremely important project to be able to deliver more secure firmware and IoT devices, follow some of these links. These two documents here in particular at the top are important. You can look at the upstream TFM code, which is entirely, it's developed in the open. It's an open source project with open source governance. You can see the Git repository for TFM here in the third link. Zephyr maintains a fork of TFM simply because of the Zephyr sort of module management policy. So our version of TFM is available here. It's generally a one-to-one mirror of the upstream TFM, and we try to repo, and we try to keep those up to date. And I put together some technical notes for myself, and just because I'm forgetful for future me, writing this presentation. If you follow this link here, you can see a gist on GitHub that basically just goes into a bit more detail and leaves it some more breadcrumbs, sort of service by service in TFM. And maybe if you really want to get into the details, this link might or might not be useful to you. And hopefully that'll help you, Release, just sort of wrap your head quickly around TFM and get up to speed to play with it. So thanks for your time, and I really hope this has been useful. I hope some of it is sort of sunk in, and that there's enough breadcrumbs to absorb some of the things that flew over your head. I really hope you'll find the project useful. I hope you'll find the integration efforts that we've made in Zephyr to make using TFM as painless as possible useful and easy. And feel free to reach out and let us know what works for you and what doesn't work for you. And thanks for your time. And yeah, just stop it with the firmware mystery soup. There are better solutions out there, and yeah, hopefully we can all sort of stop making baby steps and make a giant leap towards releasing more secure products into the wild. And again, thanks for your time, and have a great day.